everybody. For the next 2.5 weeks, we are going to be talking about our solar system. Well, we're going to be bouncing around in our textbook a little bit. I don't necessarily like the order that things are placed within our textbook, so we're bouncing around a little. But for this engagement check, we are going to be talking about our solar system, an introduction to our solar system, and about its formations. We'll talk about the formation first, and then we'll talk about sort of an intro to all those planets in our solar system. Now, before we get started on solar system formation, this I want to show you is a really cool image. It is a real image taken of a distant solar system, and this solar system is in its stage of planet formation. And we can observe these with telescopes now. And this image was the very first picture taken of planet formation in another solar system, and we have more of them since then. So this distant solar system was captured with a radio telescope called ALMA. It's called the Atacama Large Millimeter Array. It's looking in radio wavelengths to capture this planet formation. So you have the star in the middle, and we've got this disk of material surrounding the star. And everywhere where you see these sort of black, empty orbits around that star, that's where a planet has formed. That's where a planet is orbiting around that star, and it's gobbling up, it's accreting all the material in its path, and it's growing those planets. So here we're looking really at a system that truly is building its planets, just like our own solar system did more than 4 billion years ago. All of the objects in our solar system seem to have been formed at nearly the same time out of the same original cloud of gas and dust. A radioactive dating of rocks from the Earth and the Moon and other asteroids suggests an age for our solar system of 4.5 billion years. That's also about the same age as our sun. We have models to describe our solar system's formation, and any successful model to describe our solar system's formation must account for this following list of items. So we're still not 100% set in stone, you know, this process for creating our solar system, but we have some really good ideas. That's one thing about science. We keep taking more and more observations, we do more and more computations, and over time, we get closer to the truth. So again, any successful model to describe the formation of our solar system must account for the fact that planets orbit in the same direction around the sun and in the same plane. That's that flat disk of our solar system that we saw in lab a couple of weeks ago. We also have 4 inner planets, which are rocky, and 4 gaseous, liquid, icy outer planets. So this theory has to be able to explain those. We have to explain compositional trends in our solar system. Compositional trends means to explain what things are made of, because different parts of our solar system are made up of different compositions of material. And we also see that all solar system bodies appear to be around 4.5 billion years old or less. So this theory has to support that. And we also have these other kind of bits and bobs details that this theory has to support. We've got the structure of asteroids, the cratering of planetary surfaces like our moon, detailed chemical composition of surface rocks and atmospheres, and more things we have to explain with one single theory for the formation of at least our solar system, which we think must, be similar in other solar systems as well. So we find that the majority of our solar system is composed of hydrogen and helium, and that material is contained mostly in the sun and the Jovian planets. So those are the large gaseous planets like Jupiter and Saturn. The other 2% of the mass in our solar system is just made up of everything else, everything other than hydrogen and helium. When looking at the universe beyond our solar system, we also find similar amounts of hydrogen, helium, and other elements. So 71% of that, like 98%, is hydrogen. Hydrogen is the first element on the periodic table. The next element on the periodic table is helium. So 27% of our solar system is made up of that. And then the other 2% are all the other elements. So, we're made up of carbons and silicons, and we breathe oxygen. And so all those other things, gold that our jewelry is made up of, all that other stuff that isn't hydrogen and helium only composes of 2% of the mass in our solar system. In the very beginning of our universe, only hydrogen and helium and a little bit of lithium was there. Nothing else yet on the periodic table had been created. We need other processes. Throughout our universe, there were then clouds of hydrogen and helium. But as these clouds began to cool, they also began to contract on themselves, and due to something called conservation of angular momentum, which is what you saw me do when I sat on that stool and I had the masses and moved my arms in and out. Whenever you contract, you also can start to spin. And so collapsing and spinning, we're able to create the first stars out of these original clouds of hydrogen and helium. So once these first stars used up all the fuel in their core, which at that time was mostly just hydrogen, helium, lithium, they died, and they created other elements higher up on the periodic table. And then they spread these elements back into space, from which new stars are going to form from new clouds of gas and dust made up of other elements. When we observe the abundance of elements in our part of the Milky Way galaxy, we find that the abundance of elements agrees with models of how stars use their nuclear fuel, the fuel in their core. So here we have a chart that has on the vertical axis the abundance of an element in our part of the galaxy. And then we have on the horizontal axis the atomic number. So the atomic number of an element is the number of protons that it has in its nucleus. We start with 1 proton in the nucleus of an atom, that gives us hydrogen. 2 protons in the nucleus of an atom gives us helium, 3 lithium, 4 beryllium, 5 boron, 6 carbon, and so on down the line. Okay, so the taller the bar, the more abundant that element is in our part of the Milky Way galaxy. Okay, so the 10 most abundant elements in our part of the galaxy, we've got hydrogen as number 1, helium is number 2. So the current leading theory for how our solar system was formed is called the solar nebular theory. This theory suggests that our entire solar system was formed from gas and dust in a nebula. So a nebula is just a fancy word for a cloud of gas and dust. Here is an example of a nebula. There are many, 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 many nebulas in our galaxy, in the universe. It just means a cloud of gas and dust. So we formed from one of those clouds of gas and dust. The nebula that formed our solar system was originally about a few light years across in diameter, and it had a mass of about twice that of our sun. Our original solar system nebula was in something that we call hydrostatic equilibrium, which means that the gravitational force that wants to pull everything together was balanced by this pressure force outward that's caused by the internal heat of the original nebula. But eventually, that gas cloud is going to cool off a little bit, and it's going to start to become more dense. And then its gravity is this force of gravity is going to start pulling inward on itself, essentially collapsing that cloud inward. And whenever you pull something in, the big mass, and you start to collapse it, what happens is that as it begins to contract, it also begins to spin. It spins faster and faster and faster due to something called the conservation of angular momentum. So momentum is your mass times your velocity in a straight line. Angular momentum is also proportional to your mass, but times your properties that contribute to your rotation. And I demonstrated the conservation of angular momentum in a previous engagement check where I sat on the stool and had the masses and I brought them in toward myself. And as I did that, I started to spin up. So you could imagine that as being the solar nebula, and I start to collapse in on myself. I'm pulling matter in, and as I do that, I can start to spin myself up. As a result of that spinning and rotation and conservation of angular momentum, the original solar nebula that we could approximate as being like a blob or a spherical shape starts to flatten out, and that forms the disk of our solar system. It's like you take a ball of pizza dough and you toss it in the air, and the more and more you spin it, the more and more it stretches and flattens out. That's what's happening here. And the matter, as our cloud was collapsing, the matter started to migrate in toward the center of the cloud, towards the center of this disk. And as it did that, it gained speed. And when it bumps into other matter, the friction turns some of that kinetic energy, which is energy from motion, into thermal energy, energy from heat. And it starts to heat up the disk of our solar system. Now, the material at the center migrated inward the fastest, so the center becomes the hottest. The center of this disk becomes the hottest. And then you've got all this material, super dense, super hot, in the center of this rotating disk. And the central hot area, in kind of the central bulge here, is what we call the proto-sun. It's our baby sun. It will eventually become the sun that we know today. This disk is what we call a protoplanetary disk. This process that I'm describing right here is exactly like that image that I showed you at the beginning of this mini lecture. This is where, and within this disk is where all of our planets will begin to form. Now we're going to talk about why the planets in our solar system have different compositions based on their distance away from the sun. Okay, and it all has to do with the temperature of the disk. So the inner disk, all the material closer to the sun, is going to be a little bit hotter. All the material further away from the sun is going to be a little bit colder. Now, different materials condense at different temperatures. When something condenses, that means it becomes a solid. So for instance, water in its condensed form is ice. The sun kept our inner solar system, inner disk, really, really, really warm. Too hot for anything except for rock and metal to condense. So in the inner part of our solar system, we've got 4 inner planets that are rocky planets, and they were able to condense even though it was such a warm temperature there, okay? But closer to the sun, it's again warmer. So the lighter gases like hydrogen and helium, our smaller inner planets, didn't have enough gravity to hold on to some of that lighter gas, and that lighter gas just wouldn't stay attracted by gravitation to those planets because that gas was just too hot, okay? But as we get further and further and further away from the sun, the temperatures get colder. Also, the planets get a little bit bigger as we go further out, okay? So still further out, it's still cold, you can still condense rocky matter, and so all of our outer planets have rocky cores too, but they're a little bit bigger, and so they were actually able to hold on to hydrogen and helium gases. It's a little bit colder there. Those hydrogen and helium gases weren't bouncing around as much because they were a little bit colder. And so further out from the sun, because it's colder, you can get those planets to start being able to hold on to hydrogen and helium in their atmospheres and build up these thick, heavy atmospheres, okay? And that's why our inner planets are mostly rocky and our outer planets are gaseous and also icy. So we have Uranus and Neptune that are on the far edges of our galaxy that also have a little bit of gas, but they're also pretty icy too. They have some ices on them as well, because the further away we get away from the sun, the colder it's going to get, and then different materials are going to condense out. Here's an image, I think it's also in your textbook, that shows the different materials that condense out at different temperatures. They become solids at different temperatures. So when we're really close to the sun, and our terrestrial planets here, we're looking at Mercury, Venus, Earth, and Mars. Those are our rocky planets. So there, the temperatures are such that everything to the left of Mars here would be able to condense out at these temperatures that you see down here, become solids. Okay, so here we've got, metals, irons, silicates, which are rocky things that are able to condense in our inner solar system. But it isn't until you get out to Uranus and Neptune and Pluto that water and ammonia and methane start to condense. And so out here, out where we have Uranus, Neptune, Pluto, you can have ices that are of the form of water, ammonia, and methane that can condense onto those planets too. So we've got our inner rocky planets. We've got our Jupiter and Saturn, which are what we call gas giants. And then we have Uranus and Neptune, which are icy giants.